So coming to my topic, that is 4D printing of safe memory polymer via extrusion additive manufacturing, effect of orientation on various thermal properties and its optimization. Coming to the second slide, introduction. So 4D printing is a method of printing a part layer by layer by using a smart material which can change its properties over time when an external stimulus is provided to it. So basically we have a 3D printer, we have a smart material, and whenever we are providing some stimulus, it can change its shape, size, properties, then we can get a 4D printed part. Now coming to the timeline of 4D printing. So the 4D printing started in 2013 by Professor Skylar Tibbets of MIT Self-Assembly Lab. Then from that year, a lot of development have been done, and from various universities worldwide. So here we can see that there was a 4D printed implant airway splint that can grow with the growing child. Apart from that, recently there are a lot of development in the 4D micro and nano printing. Now coming to our 4D printing research journey. So we started in 2016 by embedding the smart material into the 3D printing and creating a 4D printed part. Apart from that, we also created some origami structures, some smart grippers in 2017. Then from 2019 to 2022, we focused on printing of safe memory polymers and testing its safe memory characterization using some low cost characterization methodology, and also creating some programming strategies. Apart from that, we also study the effect of process parameters on 4D printed parts for two different programming strategies. And in present we are also creating some kind of safe memory polymer nanocomposite which can have application in the areas of micro robotics, biomedical as well as photonics. Now coming to the basics of 4D printing. So 4D printing can be classified into three. The first one is the embedding of smart material during printing. The second one is the printing of single smart material, its blend or its composites. And then third one is the printing of multiple smart materials, its blend and its composites. So in the present study, I am focusing on the second classification, that is the printing of single smart material. Now coming to the process of 4D printing. So the process of 4D printing starts with the selection of the right smart material. So in the present study, I am considering a polylactide based safe memory polymer. Then comes the energy source. This energy source is nothing but the passive energy sources like heat, gravity, pressure. So here in my study, I am considering heat. Then comes the precise positioning, which we generally also say is designed for 4D printing. So here we can also consider some of the origami structures, auxetic structures, but for the present study, I am considering a bending and folding actuator. Now coming to the two programming strategies that we can have in the 4D printing using FDM. So here we can see that, just a minute, I will just click on my pointer. So here we can see that the first programming is programming after printing. So this programming after printing is a process which is generally same for all kind of safe memory material. So here first of all we have the material, then again we have to heat it and then fix it in the fixture, and then we have to heat it above its glass transition temperature. That temperature is also called programming temperature, and then from that temperature we have to cool it or quench it. Then once that is completed, we can complete the programming step. Then we can go for the recovery. In the recovery step, simply we have to provide some deformed shape, and then from there, whenever we will be heating it above the glass transition temperature of the polymer, then it can recover its shape. But whatever this post processing we are doing, which is a separate step and also requires efforts and money, we can do it using programming during printing. So programming during printing involves a process that is called FDM 3D printing process itself. But how the process works? So here first of all we have the safe memory polymer which is fed into the extruder, which is heating the polymer into around its melting temperature. So the polymer heating which was done here in this second step, so it is also getting done here. Apart from that, the material that flows from the nozzle into the print bed gets deposited onto the print bed. So that fixing part is also getting done here. Apart from that, that fixing can also be controlled by controlling the CAD model. So here we can say that the this fixing and heating part is getting done simultaneously, and then whenever the polymer filament is deposited onto the print bed and the nozzle goes up by printing different layers all together, then we can say that the lower layers gets cooled So this cooling is also getting done here, this cooling part. So here the whole programming process that we generally do for any smart material as a separate post process is getting done here. So that is our motivation why we are using a FDM 3D printing for processing of safe memory polymer. Now coming to the economical 4D printing characterization method. So here we have considered a hot water actuation testing setup. Apart from that, we are also considering an angle measurement scheme by some video processing softwares, and we are calculating the safe recovery ratio, safe fixation ratio, and safe memory index. Now coming to my topic today, that is the effect of design parameter and post-process parameter on the safe memory properties of 4D printed PLA-based safe memory polymer and its optimization. This is the complete flow of my presentation. So here we can see that we are using here the FDM 4D printing method, and then from both the methods of programming, I am using the programming during printing. And then we are going for a thermal characterization method, where we are considering different methods like DSC, that is differential scanning calorimetry, TGA thermogravimetric analysis, DTA, that is differential thermal analysis. So by using these techniques, we can find some of the ranges of temperature like glass transition temperature, crystallization temperature, melting temperature, degradation temperature, and we can go for this design parameter, where in the design parameter we are also considering the flat, on edge, and upright. So by considering these process windows that we have got from the thermal characterization, and by different printing orientations, that is a design process parameter, we are optimizing the preheat temperature. So this preheat temperature is a temperature that we provide a safe memory polymer to go to to deform it to some temporary shape. So that preheat temperature we are using a DOE based RSM methodology to optimize it. And then again, by considering the same design parameter like flat, on edge, and upright printing orientation, we are also optimizing the recovery temperature. Now coming to the experimental process. So the experimental process is same as the programming during printing. So we have the 3D printed safe memory polymer, which we consider that during the 3D printing only it has been programmed. So whatever the safe, like it is now 180 degrees, so it has programmed to be 180 degrees. Now coming to the second step, that is the preheat temperature. So here we have to heat the part because it is already programmed, so we have to heat the part and we have to deform it. So this heating we have to choose precisely that the preheat temperature should be the temperature which should be enough to bend it without any fracture, but it's not provide that temperature which will create the recovery. So for that we need to choose the preheat temperature wisely. So apart from that, we are measuring the deformed angle so that we can calculate the deformation error. Apart from that, we are also considering the safe recovery temperature. So this recovery temperature is the temperature which is provided to the safe memory polymer so that it can recover back to its original shape. So this recovery temperature also plays an important role, and if not chosen in right values, then we can also consider a recovery temperature which will program the part, that is the temperature above the crystallization temperature. So we don't want to do that. That is why we are here we are optimizing the preheat temperature as well as recovery temperature. Now coming to the thermal characterization. So in the thermal characterization, we have used differential scanning calorimetry to find out different temperature ranges. Like here we have found out there is an endothermic peak, first peak in an endothermic peak. So that is the TG, that is the glass transition temperature at around 65 degrees Celsius. Then we have got an exothermic peak, that is the crystallization peak at around 104 degrees Celsius. And also we have again got an endothermic peak, that is for the melting temperature of the PLA based safe memory polymer. Apart from that, we have also checked the thermal stability by using the thermogravimetric analysis. So here we can see that there is a reduction of 97.9% weight from the temperature 296 to 369. So we can say that the degradation starts at around 296 degrees Celsius and ends at 369 degrees Celsius. Now to find out which is the temperature that provides us the highest degradation rate, we have done the first derivative of thermogravimetric analysis, that is DTG. So here we have found that the maximum rate of degradation is around 349 degrees Celsius. Now coming to the DTA, that is the differential thermal analysis. So this is a different kind of method. Like in DSC we use the heat flow. Here we check the difference of the temperature between the reference, that is alumina. Here we have considered and our sample. So here it is a secondary test to just check that whatever result we have got from DSC and TGA, that is same or not. So here we have got the result that Tg of the 4D printed PLA safe memory polymer is around 66 degrees Celsius. The cold crystallization temperature is at around 97 degrees Celsius. Melting temperature is at 172 degrees Celsius, and the decomposition temperature is around 350 degrees Celsius. So it is in good agreement with the previous result that we had got using DSC as well as TGA. Now coming to the preheat temperature. So the preheat temperature is the temperature provided to the safe memory polymer parts before deformation to form a temporary safe. So therefore it is affecting the safe memory properties also. So we need to optimize that. So here we have considered a design of experiment based on RSM, that is response surface methodology. And here we have considered two process parameters. One is preheat temperature and the second is the time. So here we have varied the temperature from 40 to 60 because we don't want to go beyond Tg, that is the glass transition temperature. The reason behind it is that if we go the temperature near Tg or above Tg, then recovery will take place. We don't want to induce recovery before recovery cycle, and just we want to make the polymer flexible enough so that it can bend easily. So for that we are using the temperature range from 40 to 60. So here we are also varying time, and we have varied time from 2 to 12. So here it is the design metrics based on the optimal design. Now we can consider here the deformation error. So here we have considered that the deformation degrees or deformation angle should be around 90 degree. But here this is the theta d, that is the degree that we have obtained by experiments. So here we can see that theta max minus theta d, we will get the deformation error. So now our objective of the optimization is that to reduce the error, or that is to reduce the small e. Now we have done this for all the three orientation, which is the design process parameter. So for the flat case, where we have printed the part in a flat orientation. So here we can see that we have got in the ANOVA table, we can see that the model is significant as we have got a p-value which is 0.0013, because here we have considered a confidence level of around 95%. So here we can see that the p-value is less than 0.05, so it is significant. And from the process parameters, its interactions and the square term, we can see that few of them are also important, and but who's means among them who is more important, we can find it out by ranking them. So this ranking we can see in the Pareto chart. So in the Pareto chart we can see that the most important process parameter and its interaction or its square value is here, that is first one is A, that is temperature. So the temperature is the most important process parameter, and then comes its square value, like temperature into temperature, and then comes the time. So this is the ranking of most important process parameter affecting the output, that is deformation error here. Now here we can see also the normal probability plot, and we can see that the values that we have got as our output is close to that probability plot. And here we have also got a R value of around 99.46%, which is very high. And also, as we have considered more than one process parameter, we have considered the adjusted R square, so which is around 98.56%. Here also we have got that predicted R square is around 93%. So the model that we have created here and the regression equation that has been obtained here can be used for prediction as well as for optimization. So now we'll go for the optimization. So here we have considered a desirability functional analysis based optimization. So here we have considered the optimal solution by considering the objective function as to be minimum. So here we have got the optimum result, that is at around 47.52 degrees Celsius for 12 minutes. So this is the case for flat oriented part. Now let's go to on edge part. So here for the on edge part also we have done the same thing, and here also we have got the model is significant and the adjusted R square is also high as well as the predicted R square is also high. Now coming to the Pareto chart, here also we can see the most important process parameter is A, that is temperature, and then comes its interaction and then the time. So here we can see that we have also used this regression equation and optimize this process, and here we have got a result of around 50 degrees Celsius for 5.78 minutes. So here we can see that this is the 3D plot between time and temperature and deformation error. So here we can see that whenever we are increasing the time and increasing the temperature, that there is a deformation error in the positive direction, sorry, in the negative direction. And when we are decreasing it, we are getting it in the positive direction. Now coming to the upright sample. So upright sample also we have got similar kind of result. So here we have got that the temperature and time, that is the optimum, is around 48 degrees Celsius and for 7 minutes, around 6.88, that is 7 minutes. So overall, if we consider a part which has been oriented in all the three directions, then we can take one value that is 50 degrees Celsius for 10 minutes. That is our result that we have got it from here. That is the optimum parameter. We have also done some confirmatory test and it is working well, and so the part is deforming and it is not going to the recovery state. Now coming to the recovery temperature. So the selection of the recovery temperature range is from the thermal analysis that we have done before. So here we are considering the minimum is Tg, that is the glass transition temperature, because we know that above glass transition temperature only the safe memory polymer that we have considered here, PLA, goes from the hard to rubbery state, and then that is why we can also get the recovery after this. And also we are not going beyond TC, that is the crystallization temperature. So we are not going beyond the crystallization temperature, because we know that when we are going beyond the crystallization temperature, at that time the amorphous region as well as the crystalline region within the semi crystalline polymer like PLA safe memory polymer is very chain orientations are open, so it can orient in any direction, and whenever we are orienting at that time, so the programming is getting done at that time. So that is why we are not going beyond the crystallization temperature. So we are varying our temperature between 60 degrees Celsius to 100 degrees Celsius. And here we are also considering the angles, that is the angle measurement schemes that we have done in some of our previous studies. So we are utilizing those to find out the safe recovery ratio. And also here we are considering the recovery rate by considering the recovery time from the video analysis software, and we are considering the recovery rate, so that we can find out which temperature provides us with the highest recovery rate, so that we can consider it for different orientations. We have done this. So we have done this for upright, we have done this for on edge, and also for flat. Now coming to the result, here we have varied from 60, 70, 80 and 90, and we have taken triplicates, and here this is the descriptive statistics. So here we have found out the mean standard deviation, and similarly we have done it for on edge and upright. Now we can understand it better way in this from this graph. So here we have plotted it the graph between the recovery rate and recovery temperature. So from here we can see that the recovery rate is highest for 80 degrees Celsius for both flat and on edge sample. So we can see that the result that we have got is for 80 degrees Celsius is the highest. So for flat and on edge we can consider 80 degrees Celsius as the recovery temperature, and for upright we can see that 70 degrees Celsius has provided us with a better result. So for upright samples, if we are printing the sample in upright direction, so we can consider 70 degrees Celsius for the recovery temperature. Now coming to the conclusion. So here we have explored the thermal characterization of PLA 3D printed sample, 4D printed samples, and here we have found its glass transition temperature, its crystallization temperature, as well as its melting temperature. We have also studied the thermal stability of the PLA safe memory polymer using TG and DTG, and based on these values we have considered these ranges, and by utilizing the RSM, that is the design of experiment based approach, we have optimized using the desirability function analysis, and we have found out that for any orientation, if we consider all the orientation and if we consider one single value, then we can consider that is 50 degrees Celsius for 10 minutes, or else we can also take the single values that we have considered for each of the orientation. Now coming to the safe recovery ratio. So here we have also optimized the safe recovery ratio, and we have found out that 80 degrees Celsius recovery temperature provides us with better safe recovery for all kinds of orientation. So I would like to thank my supervisors, Professor C.S. Kumar sir and Professor S.K. Varshney sir, and my co-author Anita Jena. So we have our team here. So we are working on different aspects of 4D printing. Now I would also like to take this opportunity to request you all to send your submissions for an upcoming book that we are editing. That is 4D printing technology principles, materials and applications by John Wiley and Sons and Scribner Publishing. So you can send it to my mail that has been provided here. So thank you. So you can scan this for any further queries and collaborations, and if you have any question, you can anytime write to me, and I'll be happy to answer all the questions. Thank you.